presentation today. Really couldn't be better because it brings us right up to date with the current story of the white salt industry. Jon Whieldon, the floor is all yours.
Thank you. Just an intro first of all. I'm Jon Whieldon. I've worked for 30 years in the chemical industry. For the last 10 of those have been spent looking after the Holford Brine field. So I make salt from the way it's made today. And it's been really, really interesting to listen through the presentations today and hear about how the pioneering efforts have developed the techniques over time to get to where we are today. So I can give you a little bit of an insight as to how we do it nowadays, but they're founded on all those other efforts in the past from those pioneers. Also founded on the geology, and a great lesson in that earlier on in terms of why we are here as an industry. We're here as an industry just because of the geology, essentially. So specifically what I want to cover in the talk today is the development of controlled brine extraction techniques, and there's a distinct difference between those and the wild brining activity. So it's to take you through those and help you understand how those techniques have been developed and what we do today. So in terms of the evolution of brine extraction, brine and water businesses in the northwest since 1874. There was the Brine soda ash process. I think linked in with Murgatroyd, so lots of activity at the time, feeding into sodium carbonate manufacture and chlorine and caustic manufacture. In 1926, ICI was formed from a grouping of 4 different companies. One of those was Brine. They were responsible for that in this area. And ICI then became the largest manufacturer in the UK. So INOS bought that chemicals business from ICI in 2001, but has since formed a joint venture with Solvay, chlor-alkali business. Solvay developed a process for soda ash that's used here in Northwich in collaboration with ICI. So we have been partners in the past. We've worked together, and there are now 13 major sites dotted around Europe within that business grouping. So what you can see, and as I've spent my years working in the company, I've worked on the downstream plants, but I've now moved myself back to the source of the chemical industry, and really brine is a major feedstock through into the chemical industry, and a lot of that is found here in Northwich. If you want to go on to the next slide. Just a few facts. Most of what we're made up of is salt, sodium and chlorine, the 2 elements here there. Lots of biblical references, so it goes back a long way in terms of uses in food and medicine. I don't know whether you're aware the term salary comes from Latin, the Roman term, and it was considered to be as valuable as gold at some time in the past. And you'll notice if you look at a map that there's quite a bit of salt in Cheshire when you realise the suffix "which" means that it was once a source of salt. There's 400 million tonnes under Cheshire alone. It's actually quite a lot more than that. This is more the accessible reserve. There's just a few facts about salt. We'll move on to the next slide. I did a rough estimate in the first part of the day in my head, just thinking about the couple of hundred cavities that we've got on the site at Holford. And if you take a couple of million tonnes of salt out of each one, there's hundreds of millions of tonnes of salt have been extracted since the 1920s, 1930s in the brine field at Holford. And yet what you can see, of course, is the brine fields on the left-hand side there. You can see the green fields of the site, and occasionally you see the infrastructure at the surface. It's spread over 2,500 acres, and we've got roughly 200 miles of buried pipework in there. So if you were to see underground, you'd see the cavities underground there, so we had that opportunity to be able to see the underground infrastructure. So it's like a chemical plant underground, essentially. The heading pipe work is what you see at the surface, and I'll explain that a little bit more in one of the later slides. I want to move on to the next step. So then, controlled brine extraction. What is it all about, and what are the key controls? The one most obvious one that I've failed to put on there, that I've realised, obviously appreciated during the day, is that wild brine extraction is all about taking the brine from underground, and the water comes from all over the place, down through these brine runs. Whereas we put the water down, so we're water pumpers, not brine pumpers, we pump the water down and then bring the brine back and shape a cavity. So that's how the technique has evolved. It's one of water pumping to produce brine in a controlled way. In order to do that, we need to connect in existing infrastructure, so that 200 miles of pipe that's underground, we've got to connect into those parts of our brine field so that we can bring a new borehole on work. And we have to identify where the borehole's going to be drilled. So in the top right-hand corner there's an example of what we call a pillar of salt. So key to avoiding ground level subsidence is to make sure that you have a pillar of salt underground supporting the ground. So we're mining in an area of dry rockhead, not wet rockhead, so we're putting the water down ourselves and we're taking the brine back up. So we don't have those complications of not knowing where the salt's being mined. And we can control the mining so that we make sure that there's a pillar of salt remaining that provides stability at the ground level. And that can all be calculated by some clever rock mechanicists who will work out the size of the pillar needed. As you can see there, the rough spacing is about 200 metres or so apart, and the pillars sort of sits in the middle of the cavities. So cavity spacing is a really critical aspect. Setting the downhole tubes, I'll cover in a little bit more detail later, but you've obviously got to put the water in the right place, take the brine out at the right place. I'll give you a bit more detail on that. The other controls during our 4 stages of cavity development, we've got a system called air blanketing, and air blanketing again I'll describe as we go through the process. We've also got flow and strength monitoring in there, so we monitor the strength of the brine coming out and the flow, and we can work out how much salt we've taken from the ground, essentially. It's a mass balance, and as was talked about in the Murgatroyd input, we use sonar surveys, sonar techniques. So developing a cavity is a bit like developing a baby in the womb. You can see what's going on with these sonar techniques that we've got today. Using the cavity space, so a more recent development of the business is into, over the last few decades, has been into other uses for the cavity space. It's a significant space available for use, and it's being used by the gas storage industry, and it's also used for disposal of waste. And DVO waste is a byproduct from the soda ash process that would otherwise be settled out in what's known as a lime bed. For those that have seen lime beds in Northwich, you'll understand what one of those is. It's essentially a settling area. You could also put those solids out inside of a cavity, and essentially you wouldn't even know the operation was there. There's then the post-completion cavity monitoring. So it takes about 20 to 30 years before a cavity is complete, and then we need to keep an eye on that cavity to make sure it's long-term sort of stable. I'll talk a little bit about that. In terms of some of the things that we do precise level surveys, and we also top up and run off brine. I'll explain that in a bit more detail. So those are the key ingredients of controlled brine extraction as we do it today. To move on to the next stage. So this is what you see at the surface. So this is an idea of what we've got there. So there's a meter house providing electrical supply and instrument support to the flow meters that we've got. So we've got a water feed system which goes essentially through a central tube, goes down to the cavity, and we've got an uptake pipe which brings brine back to the surface, and then that brine goes through, in the early stages of a cavity development, it goes through something called a marl pot. The marl pot's there to allow the mudstone, the red stuff, as was talked about in Ross's presentation, to drop out. Once the cavity is more mature, so it's a larger size of cavity, that mudstone will tend to drop out to the bottom of the cavity. So it will come out a much purer brine once it's been on work for a while. And then the key ingredient on the outside is we've got high pressure air. So that's key to the control on the solution mining process, is the high pressure air. And that comes down the outside of the mining tube. So that's what we've got at the surface, and that's the key infrastructure. Why is it all sat at the surface? Because we need to bring a rig in to remove the tubes and replace the tubes and carry out surveys and carry out maintenance. So everything has to come up at the surface, so the connections come out, and you'll see these features dotted around our brine field. And it's for that reason, it's for that purpose, so that we can do the operation to maintain the cavity, those sonar surveys and the like. Okay, so if you want to go to the next page, it doesn't always look like that at the surface. This is an overhead shot of the infrastructure that we're putting in. So I said there's 200 miles. This is a roughly 1 kilometre section in our brine field at the moment, where we're going to be drilling more boreholes to sink them down to get more brine, extract more brine. So we have to connect in a lot of infrastructure. So it's a significant construction project. It involves putting in roads, connecting pipework, crossing point, valves, and cabling infrastructure. That's all then buried. So we leave all the topsoil and subsoil in piles. We pop it all back on again, and then we regrow any hedge lines, and we regrow any crops. And essentially, you've got, at the end of it, you've got what you started with, and those borehole heading points will be at the surface. What I put at the left-hand side there is, from an ecological point of view, you probably can't see on here, that's the greater crested newt, which is a protected species. And outside of the Harris fencing on the construction site, we've actually got a smaller newt fence, and that's required under planning conditions to make sure that the greater crested newt is not affected by our operations. There's a lot of other potential wildlife issues and needs for surveys. We're in a rural landscape, and we're subject to all of the environmental legislation. So we do have a lot of things to consider when we're undertaking a construction activity. But once the work's complete, the ground's remediated again, and we'll go back to farmland. Okay, so we go to the next step. Here's an example of what a drill rig looks like. So it will be stationed above the borehole area, and then it will be used to drill the borehole down to about 300 metres down, between 300 and 500 metres to the bottom of the salt layer. Depends where you are on the brine field as to whether it's 300 or 500, because the salt layer tends to get deeper the further south you go. Okay, so if you go on to the next one. So here's the setting of the tubes. So there are 3 tubes. There's the outside lining tube, and that's the key one. So if you go down, if this is the salt layer here, so the lining tube is cemented in. So we drill the borehole, and then we sink in a tube and cement in that tube into the bored hole. And that allows us a pathway through to the salt layer, a protected pathway through to the salt layer. So the other tubes that go in then, we've got the 2 tubes, the one with the water in, and then the internal tube, which is the brine uptake tube. And essentially what we do there is we allow a path on the outside of the outer tube, and the inside of the lining tube, there's a path for the air to get in. So there's 3 fluids, there's air, there's water in, and there's brine out. Okay, so that's the construction of the downhole tubes, and that's how they're set. And as I say, cementing in that lining tube is the key piece of the operation. On to the next one. So this one's how the cavity develops. So if you see the picture of someone floating on the Dead Sea in the newspaper, that's about 5% strength. Saturated brine's 25% strength. So if you have saturated brine in a cavity and you put water into it, the water wants to float on the top. So if you couldn't stop it from floating on the top or push it out to the side in some way, you'd mine the roof all the time. So you have no control over the solution mining process at all, other than the location of the tube and the bits that dissolve. Okay, so in the first stage here, the air blanket's really critical. In the first 5 years, it's important to make sure that the base of the cavity is developed, so that the water that's going into the cavity works its way along the blanket of air, so it can't mine the roof because there's an air blanket there, and then it finds the walls and mines the walls away, gets stronger, becomes more dense, and then drops to the bottom and goes out to the outtake tube. So essentially what's going on, you're putting water in there, and you're precisely sending that water to the area that you want to be mined, simply by using an air blanket. So it's a technique that was developed by ICI in the 1930s. There are others in the world who use different blanketing media than air, but air is the preferred one in this location. So then over the course of the next 5 years, once the sump area, the base of the cavity has been developed, the tubes will then be reset. So during that period, the point at which the water is introduced and the brine offtake, those tubes will be set to a level that allows the cavity to be shaped, the walls to be shaped in the way that's preferred. So you then get a development of the cavity, and then in the more mature stage then, you're starting to have marl, so the mudstone drop into the base of the cavity, and there are layers of mudstone that exist inside a sort of completely pure layer of salt down there. And I suspect in the Murgatroyd scenario, it's something like a rockfall, as we would call it, that's perhaps knocked the pump away. You know, in a world such as ours today, at an industrial level, to put a pump underground, it's an expensive system to lose from a rockfall if that were to fracture the tube. And that's most likely to be what's happened in the instances discussed before. And then at the last part of life, the cavity is then shaped to give the maximum yield in terms of within the available layer of salt and the cavity spacing map that's been agreed to allow the pillar of salt to remain. So essentially we've produced a bespoke cavity to make sure we've taken the maximum amount of yield of the salt, the resource from underground, without affecting anything at the surface in terms of ground level movement. Okay, so on the next one, just
can you give us some dimensions?
very, very pleased that you led me on to my next. I was thinking as I put this presentation together, I ought to really just put some dimensions, and that's exactly the point, isn't it? Because it's a big space. I talked before there's 2.5 million tonnes of salt in a typical cavity. The gross volume 1.7 million cubic metres, which gives a free volume of about 1 million cubic metres. So that's the size of a cavity, pretty vast. And as you can see, all of that mudstone's dropped to the bottom. So rock salt that's been mined by conventional techniques is usually preferred for the roads because they talk about gritting the roads. It's the grit in there that also helps as well as the salt. Whereas you get the purer white salt once the red mudstones sort of dropped out into the cavity. And that's the Eiffel Tower. There's another one of these with the Blackpool Tower on. but I thought I'd get a bit European today. So if you move on to the next one. So controls during the solution mining process. We've got more than 50 operational cavities being monitored at any one time. We need to keep 50 available because we've got a certain flow of brine to maintain, and you can only mine the cavity at a certain rate. If you mine it at too fast a rate, you don't get saturated brine. To give you another idea in terms of metrics, you put some on a mature cavity, you put some water down in the hole, it'll come back out as brine after about 100 days underground, on average, roughly. If you put water down in a young cavity, it could be 4 or 5 days. So you'll only get weak brine from a younger cavity, and regulating the flow in a mature cavity can give you saturated brine. But that means we need to give perhaps a certain number of the cavities on work at any one time. So someone works out, clever engineer works out what's the air blanket pressure setting going to be, and that's essentially that's the solution mining plan, that and the flow of water, and then the strength on the brine. So they're monitored, and after we've removed every 80,000 tonnes of salt, we'll complete a sonar survey, and that will help us understand whether we've mined the salt from the area that we thought we were mining the salt from. And then adjustments can be made. So if you're going for ultimately 2.5 million tonnes, every 80,000 tonnes gives you a chance to optimise the process and just make sure you've got everything right. The tube movements are undertaken using a workover rig. We strip all the pipework off at the surface, and then we install a rig, remove the pipes. It's a bit like a drilling operation because they're screw threaded. So they're brought to the surface, unscrewed, and then they're screwed again and put back in underground. And they can stretch down several hundred metres underground, so it's quite a lot of weight for the rig to pull. And if they're bent in any way, you wouldn't use a crane for that operation because that's a lot of release. So you've got to have a vertical mounted machine to be able to pull the tubes. Precise level surveys. So you might have seen in the fields, if you've been around our site, our area, little lollipops in the field, they're the indicators for marker posts where we've got precise level survey points. And they've been in the ground for decades, and we use those to monitor for any ground level movement across the brine field. There's one part of the site where we're in yellow because the tenant is colourblind, and we don't want him to bump into his tractor. But apart from that, they're all in red across the site. So if you go to it's not the survey point itself. If you pull the vegetation away, you'll see the top of the survey point there, and you can connect a survey probe to that, and then it's every 5 years that we'll undertake a survey, and then over a period of time you can monitor the progress in that survey area. And we've seen very little evidence of ground level movement, and I think that's the indicator to us that it's an ultimate backstop in terms of understanding how the process is going.
Can I just ask you on that? Are you measuring the level of the ground surface or the level of rock?
You're measuring the level of the surface.
Ground surface.
Yeah. See that there's been no effect at the surface. Yeah. There are models that have been produced for solution mining that indicate, with the sort of techniques that we use, that there would be probably of the order of, over a 20-year period, of the order of a couple of mils or so of movement within the cavity area, and that's tended to be borne out by the results of our precise surveys, because we've got them tracking back now for decades through to the 1930s and 40s. We can see how that movement has gone, and it's very, very slight effects during the solution mining process. So if you go on to the next stage here, the other thing that we've got in terms of the site is the second use for cavities. So cavity space can be used for gas storage, Cavities are slightly different in design. The cavity spacing is different. They're much more sizable pillars of salt. Salt's impermeable to gas, so it's the connections between the surface and the cavity that matter. So there's extra design allowance in terms of there's an outer casing on a gas cavity that has a sensor in it to check for any signs of gas. So if there's ever a sign of gas, then there's an opportunity to do something about that whilst it's being captured within the outer casing. So it's like a secondary containment on the section that moves between the surface and the cavity. Essentially, the concept is to take gas from the national transmission system, which runs at about 90 bar pressure, and then feed that into a cavity. So that feeds into a cavity, and then when required, it's taken out, it's drawn off that cavity, but to get back into the national transmission system, it needs to be, it needs to have any impurities removed, it needs to be dried, and also then needs to be compressed back up to the pressure of the national transmission system. So you can fill the cavity direct, but you need to compress it to get it back in again. So there's a gas compression plant that's linked into this style of storage, and it's preferred for gas storage from the point of view of the national grid on the basis that it allows something called fast cycle. So you can very quickly get the gas underground, and you can very quickly bring it back to the surface again when it's needed, which is very different to some of the installations offshore where you've got a worked out gas field and you put gas back into it again. They're all low pressure. So in terms of these systems here, in order to make it work, you need to have what's called cushion gas. So you need to have a heel of gas in the cavity. So you displace the brine, you fill it full of gas, and then you need to retain that gas space. So you have to keep it padded at a certain pressure, which means you need to fill with gas, that cushion gas, before you can start the operation. And the storage is from that cushion gas pressure up to the maximum pressure in the cavity. So there's a 20 or 30 bar pressure range there to put more and more gas in or take the gas back out again. And that's essentially how the operation works. Once the operation is complete, say gas storage no longer needed in 20, 30 years' time, the operation then is to simply refill with brine, saturated brine, and displace the gas. And that's an operation that's been done before in the industry, and we're very well familiar with it. So that's the gas storage concept. If you go on to the next slide, this one talks about, I said before, there's a couple of hundred cavities being monitored, some on work, but a significant number of them no longer on work. The typical example of one not on work would be on the right-hand side, and some of them are decades old. So typically we'd strip back the heading pipe work. The pipe from the cavity to the surface is then always maintained full of brine. So those of you familiar with the head pressure concept, if you maintain a head of brine in the cavity, then what that does is it assures that the saturated brine, which isn't going to mine any further, sits underground with a certain head pressure on top of it and allows for ground stability. If you were to allow that brine level to drop, then the pressure down there would reduce, so you need to make sure you always maintain the pressure. So on a routine, we'll go around, we'll check the brine. It's a simple check on the brine level inside of the string, which is why we call it a string, sorry, the pipe, which is why we leave the heading pipe working in position. It takes roughly about 20 years after mining to become thermally stable. So during that time you find that you have to top up those cavities, and then beyond that it tends to stay stable, generally speaking. There is a further option, but it's not deemed necessary, and that would be to plug once thermally stable. Obviously you wouldn't do it until it was thermally stable. but there's the option to put, if the land were to be permanently abandoned and the mine was to be permanently abandoned, there'd be the option to fill with concrete that section from the concrete lining tube section up to surface. Obviously not the cavity, but the section, the tubular that connects between the cavity and the surface. So if you go on to the next one, this is a map of our precise level survey points on the site. We've got several thousand, and we've got quite a data bank. If I look at the geological map that was put up earlier by Roz in her input, King Street's here on the left-hand side, and the sort of wet rockhead area goes across here, and the data bank of information we have is in the dry rockhead area here where the salt's deeper, and that's the salt that we mine. Okay, if you go on to the next one, I'm hoping this works here, but this is something that was produced by SOCON, who managed the sonar survey development. So they developed the probes, and they produced a virtual brine field with real sonar survey information for cavities. So what you can see as we go down into it is you'll see real survey information for the cavities. So these cavities that's essentially the real thing, as opposed to what I showed you on the diagram. They're examples of real cavities, and the shaping is unusual. So whilst we do try and shape them within a region to maintain stability, we do have to monitor them because they'll mine in slightly different ways depending on the levels of impurity underground. So you do have to make, and there's things called a finger there, so that you might get situations such as that, on that feature there, whereby you'd have a rock fall potentially if you were to mine under an area of rock and then that were to fall on the tubes and crash them down. That gives you an insight as to what a cavity looks like underground. So it's real survey data that's been put together into a model. And what you can see inside of the cavities, you can see the tubes sort of hanging down, and that's why we call them strings, because when you look at them in this way, you can actually see them dangling down in the cavity, and you can see why they're so fragile when it comes to a rock fall inside of the cavity. Even though that rock is inside of a saturated brine-filled cavity, it'll still cause quite a lot of damage because it'll be pretty sizable. So if you go on to the last slide, really that's all I've got in terms of input today. So thank you very much, and any questions?
I think that's the icing on the cake, that sonar. Any quick questions, please? Oh, lots of quick questions. Right. Philip, you're...
Just a quick point, John. When you look at the precise level, the number of precise levelling points, it is a huge number of points. I was involved in the mathematics of this almost 50 years ago. And you end up with a vast number of overdetermined equations. The mathematics for this was dealt with in the early 30s, in the days when you had to solve problems like this using computers, rooms full of very highly trained ladies with facet machines. And the mechanisms for solving them were very cleverly designed to minimise the number of turns of the facet machine.
Yes. Thank you for all that work.
Can we move... let's have two from the back, please. Yes.
All right.
Diana.
The brine field that you've described, that presumably is in production, and is that feeding brine to Castlemakelma Works, which is INOVYN Works?
It's in production today. It's feeding the pipelines that Andrew referenced before, and just to give you an idea of scale again, roughly 3/4 of our brine goes down those pipelines. So you're talking about upwards of 1.5 to 2 billion tonnes of salt moved down an underground pipeline between Northwich and Runcorn.
Yes, going under junction.
So there'll be a lot of barges and or quite a lot of trucks. Really, is the other way of looking at it. But in terms of the scale of the operation, yes, it does feed that brine today. Yeah.
Another question back there, sorry.
Gave us full detail of how you operate putting gas in the cavities.
Yes.
But you glossed over how you dealt with the DVO waste. Is that actually as a powder and is it
Okay,
covered
sorry.
down pipes?
My apologies. Yes, the DVO waste. Essentially, what we've got is a route for brine to feed through into the site at Lostock, and then it picks up the DVO waste, which is settles out into a slurry, and then that's in a slurry of brine. That solid waste, it's about 5% slurry. So weight slurry, it then it pumps across the slurry into the cavity, and then when it reaches the cavity, a bit like the marlstone, a bit like the mudstone, it just drops down to the bottom of the cavity, and then the fresh brine comes off the top, and that's just a circuit then. So we just pump that circuit round and transport the waste in a pipeline as a slurry. And a couple of things we need to just keep an eye on. We do still survey the cavities. It's the brine strength is critical, so we must make sure that we've maintained the brine strength. So if it needs to be saturated brine, otherwise we'll get problems with that operation. We'll start to mine the cavity, and the cavity is already complete, so we don't want any further mining on that cavity. And the other thing is, in terms of regulation, we're regulated for waste disposal, so we need to make sure we keep good records of the quantity of waste. There's a tax, a landfill tax that applies to that. It's classed as an inert waste. It's essentially calcium and magnesium salts, byproducts from the soda ash process. And so we're taking the salt out of the ground and replacing it with another salt, essentially, as inert waste. So it's classed as
I
inert.
think wasn't the infilling under Northwich done with partly this stuff and something else?
I think that was all pulverised fuel ash. I don't think any DVO went into Barrett's Key.
Okay,
No.
fine.
No, I mean,
Excellent, thank you.
Question here, question there, and then that's, yeah.
Just information, like I was project manager for the infilling of the mines at Northwich when I worked with Barrow Council. It's right, we did some experiments in the late 90s as to whether lime waste slurry could be used instead of PFA, which was the eventual material that's been mentioned. And that was carried out on the lime beds at Lostock by mixing the lime waste with a certain amount of cement and to see whether we would be able to get the kind of infill material into the mines that we eventually used. But that was discarded in the end, and as has been said, we used PFA in the end.
Yeah, I'm guessing there's a capital cost required to get it in the form that you need it in.
That was one of the issues, and also transporting it from Lostock to Northwich in the way of laying a pipeline and all those sort of logistical issues, as well as the actual chemical composition of the lime waste coming out of the cement.
Question there, yes.
One of the earlier speakers said that one of the uses for the salt cavities was storage of aviation fuel. Is that still?
It's actually owned by the government. Comes under the Ministry of Defence within the government. It's no longer used as a site, but it does have some remaining material in it. They're looking to decommission the site, but that's probably going to be it's storing crude oil at the moment, and there's a very, very small amount left, but a small amount in a large-scale operation like a brine field can still be a significant quantity. So to remove that significant quantity, they need the oil price to reach a certain level before it makes sense. Given that they're government funded, it's one of those things around, where's the money come from to do the remediation work? But it's on their books for remediation at some point, and the intention is to remediate. So that's their intention essentially, which is to displace the remaining oil, and then with saturated brine, and then you've got a very similar situation to the situation we've got on our post-production boreholes, where you've got a brine-filled cavity with no remaining oil in it.
What's a question here at the front?
It's a two-in-one question, really. At Salford, where do you get your
seen that coming in. And we also take from Winsham Brook.
Yes.
And we have the facility to take from so Acton Cliff, so Acton Brook, just above just above the A49, the pumping station there. So there's 3 different water courses, and if we're getting a real emergency, we can take it out of the Trent and Mersey Canal by agreement for a period of time, because you can often find that in certain situations there's an excess of water within the Canal Rivers Trust, and they can move it around the country in the canals, and we otherwise rely on these pumping stations at abstraction points. So we take quite a lot of water out to produce the level of brine that we make.
The second part of the question was that abstraction of water in any way compromised by the old uptell works that lost out? Because there was a lot of public opposition when they disbanded the factory by cleaning the sites of the possibilities of leaching into the leaching into the water.
Yeah, we don't take water from boreholes. We take water from rivers, which are so it's not in the same way as you would take from the water table.
You've actually monitored for lead content as well.
Well, we would do in terms of what we take from the rivers, but it's not what's in the water table. I wouldn't be able to tell you what's in the water table. And
Chris, is it a quickie? You seem bursting to ask.
You mentioned fast cycling. I just wonder if the audience would like to understand what that means. There's a critical job. I don't know if any of you wondered how wind power, with all its variations, actually gets accepted onto the UK grid. Wind farm output goes up and down over the hour, over the day. Quite often the fleet's only producing 1% of its rated capacity. At other times it almost reaches 90% of what it's supposed to do. Despite all the hype in the press, batteries to smooth this out are simply not affordable on the huge-scale wind farm. So what actually happens is when the wind goes down, gas turbine plants have to jump up, because something's got to be doing the opposite of what the wind's doing in real time, minute by minute, hour by hour. That requires the gas fuel rate into these stations to change enormously rapidly, and that is what's giving INOVYN such a good business on their gas cavities and the other purpose-built ones, the British Gas Filter ones in Yorkshire. Without them, the system simply wouldn't run, and we wouldn't be able to use wind power on anything like the scale we are. That's what you'd like to know.
So I now know what fast cycling is as well.
It's absolutely critical.
well, I think just to distinguish between other forms of gas storage and fast cyclists, the other form of gas storage would be winter to summer. So
yeah, that's for all your central heating boilers. You use 5 times as much gas on a winter morning as you do in midsummer. That's done by the big underground gas fields. So the volume in these gas fields is maybe 70, 100 times the size of Holford, but it can only come out relatively slowly over winter season.
But because it's slow to come out, it can
That's
still come out when you
volume,
need it in the winter, but it's obviously slow to come out.
Yeah.
So it doesn't, you can't be instantaneously turned on.
No,
Okay, I'd like to thank John. As I promised you INH to honour. Thank you very much, John. Thank you very much.